Hey everyone, in this video I want to go over an approach to orientation warping that's different than the approach I took in my distance matching tutorial series. It's a new system that I've put together for my own game that I'm working on, and I wanted to go ahead and share it with you guys because I think it is a much better system than what I came up with for the distance matching series. The project files, the plugin that I use, and the animations will all be linked down in the description. You can download the animations and the plugin and copy my blueprint logic over into your own project, or you can just download my project and copy and paste its code, mess around with it, do whatever you want. I just wanted to share this system with you all. Let's get started. Before I hop into the animation blueprint and begin walking through it with you guys, I wanted to go ahead and show you all an example of the orientation warping setup in action here. So this setup is using two animations like the setup in my distance matching series, but the main difference with it is that I'm only using one orientation warping node. There aren't any separate states, there isn't a whole bunch of blending, there's just one node, and it doesn't matter what animation you input into it, it will give you the proper orientation angle. As you can see here. Right now, it's inputting a forward animation, and we're using that to run towards, to run right. Using the backwards animation to run left, and these look like they could be complete left running animations and right running animations. And of course, it'll give you everything in between. One thing I forgot to mention before we get started, I'm using a template third-person project. I'm using the template third-person character and the template third-person animation blueprint. There is one more thing that I forgot to mention when I was originally recording this video, and it is that the animations that I'm using, the two of them, the running forward and running backward animations, are linked in the description to download along with the project and the plugin. Once you import the animations into your project, you'll need to make sure that you enable root motion and force root lock, because these are root motion animations here. And the other thing you want to make sure you do is inside of the animation blueprint, under edit defaults, make sure you're taking or root motion for montages only, or ignoring root motion. Anyway, let's get back to the video. So let's just hop straight into it. I'm going to start with my animation graph. We have a state machine, inertialization node, and our output pose. And our state machine is pretty simple. We have two states, idle and run. Their transitions are both set to inertialization at 0.2 seconds. We're checking if we are accelerating, and if we are transitioning from idle to run. And if we are not accelerating, we are transitioning back from run to idle. That'll explain how we get this variable and set it later on in the video. Our run state is our most complicated state here. We have this in run forward animation and this in run backward animation. We're blending them by a forward boolean. Again, I'll show you how I got this boolean later in the video. It is an inertialized blend set to 0.2 seconds. And then we do our orientation warping. And I am using the free custom anim node plugin. I will give you a link to download it in the description. And then all you need to do is go into your project folder, create a plugins folder, extract the custom anim node zipped file, and then grab the actual custom anim node file from inside of it, place it inside your project, and open up your project. It'll ask you to rebuild the plugin. Go ahead and do that, and you'll have the plugin in your project. And then so you just search it up inside this plugins window and enable it. Then, so we're using this orientation warping node. There are some settings here. I've set the body orientation alpha to 1. I've added 5 array elements to this spine bones array: spine 1, spine 2, spine 3, neck 1, and head. For the IK root bone, for the IK foot root bone, I've selected IK foot root. But the great thing about this setup is that you don't necessarily need this orientation warping node. You could use an orientation warping node from Unreal Engine 5 if you want to do it inside of Unreal Engine 5. There's a built-in anim warping plugin that has the same functionality and probably better than this. There is a paid plugin on the Unreal Engine Marketplace called Strider. It's fantastic. It has orientation warping, and if you use it, you don't even have to use this interpolated locomotion angle variable. You can just do these smoothing inside of the node itself, or you could just build out your own blend logic with some transform modify bone nodes and rotate to your legs, torso, and all of that with this interpolated locomotion angle variable. It's only one variable. The logic is fairly simple, and so you can swap out any orientation warping method you want to. For next week, I'll try to set up a completely procedural approach to this orientation warping so that it doesn't even need to rely on any plugin. But for now, you can use the custom anim node plugin that I'm providing in the description. And that is our entire animation graph. Now, in the event graph, I checked in a sequence node right after event blueprint update animation, plugged then 0 into the is valid that was already there, and then from then 1 I dragged off into all of my own code here. This is all the code that is required to get this working, and it might look a bit complex, but really it is simple. I'm going to walk you guys through everything, and all of this up here even is just to draw a debug arrow to help visualize things later on. So we're going to get a player character variable that is a reference to the third person character blueprint. And we're going to actually make this a validated get. And to do that, you get a regular get, right click, convert to validated get. So now we're checking if this is valid, if this is set with a value, with a player character reference. If it is not, we're going to cast to the third person character and set the variable again to make sure we don't run into any issues and that things really are working here. We're going to check if that's valid. If it is, we're going to begin our code. If this is valid from the get-go, if we've already set it, so if this is the second tick, we go straight into our code. The first thing we do is we get our isAccelerating variable. We get our player character, character movement, get current acceleration, get the length of that vector. So the acceleration is in the format of a vector. So let's say we're holding down W and A. Our acceleration is going to be our max acceleration inside of our movement component. You can see our max acceleration here, but it is going to be split between right and forward. And so what we're doing is we're getting the length of the vector. So in this case, our vector is diagonal like this. Getting the length, we'll just get the length of our vector of our arrow, and that'll tell us what our actual acceleration value is. And if it's greater than 0, we are accelerating. Next, I'm just going to get the velocity with a get velocity node plugged into the player character variable. And now I'm getting two more variables that aren't in the standard third person character, a move forward variable and a move right variable. I'm setting these straight from our input access events for forward and right. I'm using our access values, and I'm making a vector out of them. And what this is doing is this is bypassing the floating point errors that you get when you calculate the direction from the velocity and forward vector and right vector, however it's done. I don't even actually recall the actual calculation currently. But that get direction, that 0 to 180, and then you have the negative 180 back to 0, that variable, that standard method, in my opinion, is flawed, because I'm sure you've all run into it. You're going backwards, and that value is flipping back and forth between negative 180 and 180. And that is because you are getting it from things like velocity, which take into account, you're getting it from variables that are being calculated inside the 3D space of the engine and being affected by that 3D space and taking your position into consideration. And so you get floating point inaccuracies. That, 180 might really be 179.99999 when it should be 180. Or negative 180. They're so close that it'll flip back and forth. And a lot of problems come from that, a lot of time in various different animation blueprints. In pretty much any setup that uses that, you spend a lot of time trying to account for that. But if you make a vector from your input values, set it as a vector, or you don't even need to set it. You can get its pitch using this node that's built into Unreal Engine, normalize the axis, and create a direction variable that functionally is the same as the direction variable you can otherwise calculate, but if you're holding down S, it's either going to be negative 180 or 180. It is never going to flip back and forth between the two, ever. So you'll never get any of those errors when you're maintaining your direction. The variable is not going to change at all. And now, this is where things get a bit more complicated. We take this direction that's on a scale of negative 180 to 180, and we are checking if it is inside a certain range. And I've put together this diagram to help explain. So we have our circle, our direction, we have our negative 180 all the way to 180. And this arrow represents the facing direction of our character. This is forward. This arrow is pointing this way when we are moving forward. Think about a regular orientation warping setup. When you're going right, you might have a animation where when you're going left, you might have an animation where you're going left, but it's like a backwards running movement. Or when you're going right, it's a forwards running movement. Most systems will do it that way when it's strafing, and this system is built to replicate that. You essentially check if your direction is inside of a range. In this case, if it is less than negative 45 or greater than 135, we will play a backwards animation and orientation warp it throughout this range. If this is not true, if it's not in this range, we'll play a forward animation and orientation warp it in this range. So the system you might be used to from Paragon, if you've watched some of the presentations some people from Epic Games have done, they have 4 animations, and you have a forward animation, and it switches at around the negative 45 and 45 degree mark, a right at around 45 and 135, and it's also like a running forward but looking right. a left that's running backward and looking left, sort of, from negative 45 to negative 135, and then a backward animation from about negative 135 to 135. And so this recreates that, but with two animations, and it orientation warps to what would be a left animation or what would be a right animation. So if it is greater than 135 or less than negative 45, if either of these are true, we know we're going backwards. So we are inverting this boolean and setting forwards with it. That is how we get that variable. We also take this, and if we are going backwards, we know that we need to use an orientation offset because we're playing a backwards animation, and so we've already turned our direction 180 degrees just by switching that animation. So we need to take that into account and add 180 to our input direction variable here if we are going backwards. And now we get our forward vector, the vector that points in the forward-facing direction of the character, and we rotate it by this new value. To visualize this vector, I've put together some code here. We're getting the actor location, and we're just subtracting the capsule half height from it so that it's at the feet, not around the pelvis area. And that's where our line starts. Our line ends. It's this vector when we're adding it onto here. This vector multiplied by 100, and that'll give us a vector that's further out to a point in space that's further out to end our arrow at. Just gonna disconnect. Whoops. That and grab a sequence and plug in this draw debug arrow. Now, when we go forward, we have this arrow and we're going forwards. We can go to the left here, forwards and left. You notice it's always going to point in our orientation. And that is my favorite thing about this system, is that you're never trying to rotate the pelvis around backwards and then unrotate it back around. It just never happens. And that, I think, is that even considering a value where you're going backwards and you're trying to rotate around to face backwards, but you need to rotate around to face forward, so you're compensating. It's just adds complexity that doesn't need to be there. We don't do that when we walk. When we walk, well, we have a vector like this and a direction, and we can either move forward along that line or we can move backwards along that line. We don't spin the line around. That line still points in the same direction. We're just moving in a different direction along it. And that is the concept that this system is built on top of. So I'll try to explain. We're taking it, and if it's less than 135, greater than 135 or less than 45, we're adding this offset onto it. And this offset is taking, when the arrow is in this range, it's adding 180, now it's back in this range again. It keeps it out of this range. The arrow can only swing from here to here, and if you want to move backwards, you switch your animation. You don't spin the arrow around because it's pointing in the direction and then try to unrotate it back. You are, but it's a much more simpler way of doing so. In my old system inside of the distance matching series, it got incredibly complex dealing with the direction and trying to keep the direction from doing weird things. So this is a much simpler system, and I'm really happy with it, and that's just why I want to share it with you guys. So we rotate this by the forward vector so that when it's 0, it's pointing where we're facing. And then we draw our debug arrow. But we don't need our debug arrow anymore. That was just for the purpose of example. Now we take that vector and, well, now that it's rotated, we stop facing 0, our actor rotation is something else, and it messes with our vector. And if we got its yaw and plugged that in, it would be a mess. So we need to unrotate it by the actor rotation. So now we are resetting it, we are unrotating it back. Actually, I don't even think that might be a bit of redundancy. Let's see if this works. Yep. Works perfectly without it. There's no need to unrotate it back. The only reason it ever needed to be unrotated back was because of that debug. The way I was building things out originally, I never stopped and looked at that a little bit more closely. So we just add 180 to that if it's backwards, and we set our locomotion angle. And that's going to be the direction that we want to face, that we want our legs to move in, that we want to walk in or run in. But if we just plug in our locomotion angle, well, there's issues. Especially when going backwards, it seems. Why is that? That's strange. Let's take our interpolated locomotion angle. Ooh, yeah. That's certainly an issue. It looks like we do need to unrotate it after all. I apologize for that hiccup there in my brain. I should know by now to not try to fix things that don't actually need fixed in my videos, that I've already done it beforehand, because I did that in the last video too, I think. So we're rotating the vector to our forward vector, then we're unrotating it with our actor rotation, and we're just getting the pitch from that vector, and that is our locomotion angle. So now we're going to interpolate the locomotion angle with a rinterp. So instead of using finterp to interpolate a float or interpolating rotators, I've just taken the node of rinterp2, and I've right-clicked and I've split both of these struct pins because we only need to deal with yaw. And the reason I've done this is, what if we're at, I don't know, 135? We need to get to negative 135. We don't want to interpolate from, well, we don't want to do any sort of linear, number line interpolation, because then we're going backwards, the wrong way around, through 0, down into the negatives. If we use a rinterp, it'll know, hey, wait, we can actually continue to rotate it in its currently, make the number get bigger. It doesn't make sense on a number line, but when you're rotating and you have degrees and 180 is negative 180 and you switch over, it makes sense, and rinterp can handle that. So a new variable, interpolated locomotion angle, is our current, locomotion angle is our target, world delta seconds is our delta time, interp speed is 5. You guys can play around with that, change it around, and we take the return value and set our interpolated locomotion angle. That's plugged into our orientation warping node, and that is the entire system. There's no fancy starts and stops or distance matching going on here. This is just pure orientation warping. I kept the animation blueprint structure as simple as I could. Feel free to take it, expand it, do whatever you want with it. I just wanted to share the system with you all. And the project files are actually going to be linked in the description, so you guys can download this project here. The plugin will be included in it. So I think that's everything. Going to take a half a minute or so and move the character around. I did a little example in the beginning, but I know that there's people out here or out there who will immediately skip to the end of videos to look for this kind of stuff. I'm one of them, and so here you go. This is the end result, and now I'm going to roll the outro. I hope you all found that video useful. I hope that you learned something from it. And if you did, leave a like, comment, subscribe to the channel, and join my Discord server. Thank you for watching, and I'll see you in the next video.